Yeah. Big praise.
Ready to start thinking after a long weekend? No. Yeah, it was nice. I hope you had a chance to relax and enjoy the weather. So I'm going to review a little bit because I'm guessing things might be a little hazy after a long weekend. So let's step back a little bit to osmosis. And I said osmosis is a two-part definition. So what are we focused on watching move? What's moving? The water. If I can get this to work. Come on, movement of water. What's part two? Through a selectively permeable membrane. So you have to have both occurring for osmosis to be taking place, right? And then last week, I think we also looked at the idea of diffusion. Remember Fick's first law? We looked at that for the idea of diffusion. Where's Fick? Fick's first law, here we go. So with, whoops, the one before it, not that one, this one, where we looked at the idea of a concentration gradient. And the delta C over delta X in that equation is getting at a difference in concentration in two parts of a system. So in our case, we're looking at what's happening on either side of the membrane. And if there's a difference in concentration, we're going to have some water movement. All right. And so we looked at that. And then we also looked at the French guy's equation, right? Poisson, I can't pronounce it correctly. Where is it? Bulk flow. There we go. Come on. Where we looked at, if you think about water movement in the plant, diffusion concepts certainly come into play under certain conditions. It just depends what part of the plant body you're looking at. But yes, think about diffusion sometimes. Sometimes you have to think about bulk flow, which is occurring usually over long distances in the plant. And that this idea helps explain how quickly water can move through the plant body, for example. And so in this case, with that equation, you have a delta P over delta X. So you have a pressure difference. In this case, we're thinking about on either side of a membrane, right? So osmosis, when you think about osmosis and the movement of water, you have to take into account both a concentration gradient and a pressure gradient to see how it's going to happen and how you're going to reach equilibrium eventually, and you'll get no more net water movement. All right, so we have to think about both of these equations. And then we introduced a third equation, right? We talked about the chemical potential of water for a little bit, and then I said plant physiologists like to convert all of that and do derivations to get you the water potential equation, which is much easier to measure in a real environment because you can take pressure measurements, and that is so much easier than trying to figure out chemical potential. So where are we? Let me get to that slide. Ooh, computer. So we talked about this as well. So here's the water potential equation, psi sub W. Water potential is equal to psi sub P plus psi sub S. And we talked about how the psi sub P is standing for the pressure potential. In our case, we're thinking about turgor pressure or hydrostatic pressure, water pressure. And then we have to think about that second component, the psi sub S, which is your osmotic potential. Basically, you're looking, the S is standing for solutes. You're thinking about how much solute is on either side of that membrane. And then based on that, you can start thinking about water movement. How is that going to happen? And so we're going to just stick to this equation. Remember, I said you could tack on a couple of extra components here, but for this class, we'll just keep it simple and think about this shorter equation. So psi sub W is equal to psi sub P plus psi sub S. Okay. Let's go back to the osmometer, or the U-tube, actually. It's more of a U-tube, not an osmometer. Let's do the U-tube. Okay, we looked at this idea, and we said, okay, we have water, we have some, in this case, glucose dissolved in the water, we have a semi-permeable membrane. So it's all set up to start thinking about osmosis. And so because we have a difference in concentration of, there's two ways to think about it. You can either think of a difference in concentration of glucose on either side, or you can look at the free energy of water on either side. It's typical that you learn about the concentration of the solutes and you think about, okay, there's more glucose on the right side of this U-tube, there's less on the left. Based on that, water's going to move over to the more concentrated side to dilute out all that glucose, right? That's how you typically learn it in intro classes, and that's fine. So here we have that happening. And so when we first thought about the water movement, it was a delta C over delta X. We're looking at a concentration gradient, right? We're saying less glucose over here, more glucose on the right. That's the difference in concentration from delta X, you know, and it's the membranes involved. So yes, we're thinking about osmosis. Then, so that kind of kicks things off. That shows, okay, yep, water's going to move in this case off to the right. And as you do that, you see it moving up the little tube. So now you have a delta P over delta X coming into play, right? Because now you have this pressure gradient. You have more pressure on this side of the system. As this water column is increasing in height, you have more pressure on that membrane than what you find over here. And so you have a delta P over delta X, higher pressure over here than here. And so eventually that delta P over delta X is going to come into play. And eventually it's going to happen where water will cease to move. You'll get no more net water movement. All right. And so when you think about water movement across a selectively permeable membrane, you have to think about both ideas. Concentration differences. Is there a concentration difference? If there is, how dramatic of a difference is it? That's going to tell you which way water is going to flow. And then as soon as water starts flowing, you start to think about a pressure gradient and go, okay, now we're going to get a buildup of pressure as the water is moving, in this case, up into the right side of the U-tube. Okay. So now let's take these concepts and frame it with the water potential equation and start thinking about how that's happening when you start involving the water potential. So we looked at the water potential gradient, and we went through this last time, and we said water moves from high water potential to lower water potential based on a gradient. But because in a plant, water potential is either 0 or some negative number, I'd like you to start thinking about the negative scale and frame it more as the idea of water's going to move from a less negative water potential to a more negative water potential. And technically that's higher to lower. Less negative is higher compared to a more negative number. But I would prefer that you say it this way when you are getting quizzed on it or in an exam, that you talk about water's going to move from less negative to more negative. All right, and I'm trying to get you to think that way because I've had students use the higher to lower terminology, and for some reason they start to get things switched around when they get into the details and they get it wrong. And so I think I haven't quite figured out, I'm not a neuroscientist, but there's something about that. And so I want you to really focus in on water moves from less negative to more negative. We measure all of this against a reference. We say if it's pure water, if it's open to air at atmospheric pressure, then we just say the water potential is equal to 0. So if you just had a beaker of pure water sitting here, open to the air, we'd say the water potential of that water in that beaker is 0. Okay. All right. Let's go, we skipped ahead a little bit. So we looked at the negative scale here, where you have 0 and the positive numbers going off to the right, the negative numbers going off to the left. And as you're on the negative scale, as you're approaching 0, that's a less negative area of the negative scale compared to further away from 0, and you get more negative values. Okay. And we looked at this idea last time, how we have a beaker with some sucrose solution in it, and we have a plant cell, and somebody did the calculations and figured out the overall water potential. of both the cell and then the beaker. So we have a negative 0.15 in the beaker. We have a negative 0.25 in the cell. So once we drop that cell into the beaker, how is water going to move? Into the cell, right? Based on the laws of osmosis, you have a delta C over delta X. And then we know that with the overall water potential, it's going to move from less negative, so 0.15, negative 0.15 is less negative than negative 0.25. So when you drop that cell in, water is going to move from the beaker into the cell. Well, as soon as you do that, this is a living cell with a cell membrane and a cell wall. So it's moving across that selectively permeable membrane. Now you have more and more water coming in that's going to exert hydrostatic pressure. So now we have a delta P over delta X to think about. So water is going to keep flowing into that cell until you have these two components. They're going to be shifting their numbers a little bit. The size of P is going to go up, of course, in the cell because water's flowing in. And so you're going to get your psi sub P value shifting. It's going up. The psi sub S. Well, psi sub S is going to be either, well, psi sub S is going to be a negative number, right? So again, you have to think about adding these together. You're really adding either psi sub P will either be 0 or some positive number. And then psi sub S is going to be a negative number. So you're going to have to add those together to get your overall water potential. So let's think about an example. So let's play with this a little bit and look at what's happening with the beaker with the solution in it, and then a plant cell that it will get dumped in. Let's work through it. So let's say before we start the experiment that you did some calculations, and let's say you studied that plant cell and you determined, oh, it's a flaccid cell. So what does that mean in terms of its psi sub P? What would the value be? Talked about this last week. If it's flaccid, psi sub P is equal to what? 0. All right, so that word flaccid means there's no net pressure being exerted against the cell membrane in there. Someone did the calculation on the psi sub S value and figured out that the overall psi sub S is negative 0.85 megapascals. So if you add those two together, you get your overall water potential, which is negative 0.85. Then someone did the calculations for the beaker. So that beaker is open to air. What can we say about the psi sub P? 0, it's atmospheric pressure. So we're just going to say the psi sub P is 0. The psi sub S, someone did the calculation, it's negative 0.25. So then you add those two together to get your overall water potential, it's negative 0.25. So that's how the situation is at the start of the experiment, before you drop in the plant cell. So based on that, the overall water potential in the cell is negative 0.85, in the beaker, negative 0.25. Okay, now let's imagine you drop that cell in to the beaker. We have the condition of osmosis because we have a selectively permeable membrane in that plant cell. And we have a difference in concentration, so you know there's going to be movement of water. How is water going to move? Into the cell or out? Into the cell again, all right? Because the beaker, the psi sub W is less negative. Negative 0.25 is less negative than the negative 0.85. So water's moving from the beaker into the cell. As soon as that happens, excuse me, as soon as that happens, you have water coming into that cell. Now you have a hydrostatic pressure that's going to be kicking into gear here. You have to consider that now, because that is an intact cell with an intact cell membrane. Water rushing into that is going to exert hydrostatic or turgor pressure. So, and let me put that all back up again. So this is what we just saw. So let's say you come back after a few minutes and you start taking measurements of what's happening in the cell, what's happening in the beaker. So if you have water rushing into the plant cell from the beaker, what's happening to your psi sub P? Is it going to stay 0? No, it's going to go up. It's going to be some positive number. Well, someone did the calculation for you, and they figured it out that the psi sub P at the end of the experiment is 0.45. That's a positive number, okay, megapascals. So if you think about water rushing into that cell, what's going to happen to your psi sub s value? You started out with a negative 0.85. Is this number going to go more negative, or is it going to become less negative as water rushes in the cell? You can hear the whispers, less negative, right? So you have that water rushing into the cell. It's diluting out the contents of the cell. So your psi sub s value is going to become less negative. It's going to be closer to 0. It's going to be less negative. So someone did the calculation for you, and they said, yep, that's true. It went from negative 0.85 to negative 0.8. This is a less negative number than what you started with. Okay, then they looked at the beaker. So then if you just add those two together, you get the overall water potential of the cell at the end of the experiment at equilibrium. So when we say at equilibrium, that just means there's no more net water movement. It's just even Steven exchange of water molecules. There's no net water movement. So let's think about the beaker. So you started before the experiment, psi sub p is equal to 0. Has that changed at all? Thinking about that beaker? They didn't come along and close the system down and create anything different with the beaker. It's just the same beaker. So the psi sub p is equal to 0 still. Okay, but we know that there's water leaving the beaker, which has a solution. So water's leaving that and going into the cell. So what's happening to that solution? It's getting more concentrated with the sucrose or glucose, whatever's dissolved in it, right? There's fewer water molecules in there now. So the glucose concentration is getting more concentrated. If something has more solutes in it now, what happens to your psi sub s value? Does it become more negative or less negative? More negative. It's getting more concentrated. That's going to drive your psi sub s more negative. So someone did the measurements for you, and they did discover, indeed, that it did become more negative. You started in the beaker with a psi sub s of negative 0.25, but it shifted down the negative scale to negative 0.35, further away from 0. That's more negative. So the psi sub s in the beaker is more negative. You add those two together, at equilibrium, the water potential of the beaker is equal to the water potential of the cell at equilibrium. So you can see how in the cell, you can see you ended up with different psi sub p and psi sub s values at the end of the experiment than what you started with. And of course, that affects your overall water potential. The beaker, there was only the shift in the psi sub s because it's open to air. So your psi sub p was 0 in both before and after. And then at equilibrium, the two parts of the system, the cell and the beaker, they have to equal each other if it's truly at equilibrium. The overall water potential has to equal each other. Have I convinced you? Questions? Ben, that's bad news for the cell. But yeah, if it bursts, then you have no longer an intact cell membrane. Osmosis, we can no longer really talk about osmosis.
But what would cause that? Because you're saying like it would stop when the pressure drops. But obviously something's done it.
Yeah, so that what's going on here is that both the psi sub p and psi sub s are coming into play. So water will keep rushing in to try to dilute out all the contents in the cell, but it can only go so far because the pressure buildup is going to go, nope, no more. I'm not, there's no more water that can get in because there's such a pressure.
Okay.
So yeah.
So that would happen if there was like pure water.
Yeah.
Okay.
Yeah. So pure water, like you can force the cell to explode if you have a solute concentration that's super drastic between the two parts of the system. I do that all the time when I used to teach BI 100. I'd have the students, so that's to non-majors, and I wanted them to get across the concept of DNA. And of course, you can't see DNA with the naked eye. So what I would do is grow up a bunch of bacteria that loves really salty conditions. So it's like huge sodium chloride solution, So that's what they're used to. So they're inside of their cell. They're really high solute. And then I would dump them into pure water in the lab. I'd have the students dump that, and that would just explode the cells, and the DNA would immediately become visible because so much would come out. It was a really cool experiment. So, and then some companies started selling, you can do that, isolate the DNA and then encapsulate it into like a little pendant that you can wear. That's a necklace. I thought, oh, well, that's interesting. But anyway, so overall water potential at equilibrium, they have to equal each other. I've had students in the past say, well, at equilibrium, wouldn't the water potential be zero? No, only in a certain condition would it be zero. At equilibrium, that means the overall water potential has to equal each other.
Would it work the same way if the beaker
So that's a really good question, because in a real plant body, you kind of have that more of a condition, right? And so if you can imagine two cells neighboring each other, and let's say there's not the plasmodesmata tunnel connection going on, they're just going to go through another part of the membrane, then you would have that condition where there would be a Sisa P in the other cell, and you'd have to play with both of these in both cells. Yeah, for sure. So this is kind of a simpler example to start you thinking about it, because the open beaker, by definition, your Sisa P is equal to 0. But if you had two neighboring plant cells, you're probably going to have a Sisa P value unless you say the word flaccid. So I'm starting out simple here. So let's say we had a beaker of water, pure water, instead of a solution. So if you have a beaker of water, pure water, your Sisa P would be 0 still, because I didn't tell you it was closed over. What would your Sisa best be for pure water? 0. Okay, so then that would be a different situation. So then your overall water potential in the beaker would be 0. So that means at equilibrium, you need to reach 0, an overall water potential of 0 in the cell as well, once it reaches equilibrium with the beaker of water. Okay, so that's a little different. So let's see, where is the other? Where is it? So here, oh no, not this one. Where is it? Sorry. Well, let me just draw it. I can. So if we have a beaker, is this going to work? Why is my touch screen not touchy? I can do it with my finger, but what do you call this thing? Stylus, right? It doesn't pay attention to my stylus. I've tried 2 different ones. So let's say you have a beaker of water. Oh, it's not open. It's open. Sorry. Well, mine's a touch screen, but sometimes it just doesn't like it. So let's say it has a sucrose concentration of 0.1 molar. Remember, we talked about this last week. So the question is 0.1 molar? Molar is moles per liter, remember? All right, so moles per liter. So moles per liter is not megapascals. Water potential is measured in megapascals. The Sisa P is in megapascals, the Sisa S is in megapascals. So if I give you a thought problem, or in lab you work through the experiment you're going to do tomorrow, you're going to have a bunch of different sucrose concentrations that you're going to be working with, and there'll be different molar values. And you're going to run an experiment where you'll collect some data and graph it out, and you're trying to find a particular molar concentration that gives you no more net water movement. So you're looking for the equilibrium point. And then once you get that certain molar concentration, you'll be able to figure out your Sisa S. But you can't directly say 0.1 molar is your Sisa S value. You can't do that, all right? Because molar is not megapascals. So you're going to learn in lab, you're going to have all these sucrose concentrations you're going to be working with. You're going to graph out your data, and you're going to drop down and find the right sugar concentration that gives you no net water movement. And it'll be some molar value. Let's say you find out tomorrow that 0.2 molar sugar concentration gives you the situation where you have no net water movement when you run the experiment. Well, then you have to plug that into what's called the Van't Hoff equation, which you will learn about tomorrow. The Van't Hoff equation converts your moles per liter with a short little calculation. You'll be able to figure out your psi sub s. My touch screen is possessed. You'll be able to figure out your psi sub s from that. Okay, so you have to do that extra step. You'll be finding, okay, what concentration of sucrose is giving me no net water movement? But that's not the end of the story. You have to plug that in to the Van't Hoff equation. That gets you your psi sub s. And then you can plug that into your overall water potential equation. Okay. And so I'm making a big deal about this because I've seen in the past that students immediately think 0.1 molar is talking about megapascal, and it's not. Okay. You still have to think about it because it's telling you how much solutes are in the system, but you have to do an equation to get you your psi sub s value. Does that make sense? Okay. Oh, my computer. All right, so I think we left off here on Friday. And I said, so we're going through all of this and talking about water potential, but what's the big deal? Why is that such a thing we should care about? And so here we're looking at the idea of as you're closer to zero, that's a more well-watered plant. And where it's a nice fat bar, that means that things are really cooking along nicely. So you have nice cell expansion, the cell wall synthesis is cooking along, your protein synthesis, yep. Stomatal conductance just means that you have, your pores are wide open, your stomata are wide open. You see photosynthesis is cooking along. But then as you get into more negative water potential, that is a situation where the average plant that's like, oh, okay, now we're getting under water stress. The plant doesn't have enough water. And so now you start seeing these bars narrow down. That means that they are slowing down. And then after about -1, you get cell expansion just totally stops. When you get to about -2, you can see that photosynthesis stops. Well, if it's in the middle of the day, nice and sunny, that's not good for a plant to have photosynthesis come to a crushing halt. And so the water status of the plant can really help you to understand the health of your plant and then the needs of the plant. Should I water now or can I wait? And if you are trying to make a profit and growing certain crops, having that knowledge can increase your profit margin. It's super important. And so having this knowledge is a good thing. Now, these top two, abscisic acid accumulation, you see is actually increasing. Solute accumulation is actually increasing. It's like, what's up with that? So abscisic acid is a hormone. We'll talk more about it later in the semester. It's called the stress hormone. It really is a misnomer because there's another hormone that's even better at being a stress hormone. But anyways, abscisic acid's claim to fame is it's really involved heavily in water stress situations. So when the plant is experiencing, uh-oh, I'm running low on water around me, what part of the plant body is going to pick up on that first? Roots, right? The typical plant, roots buried in the soil, that's where the water is. So it's actually the roots that are constantly assessing the environment. How much water is in the soil system? Do I need to grow more roots to get deeper in and get more water? What's going on here? Do I have enough water? Okay, if I do, great. Let's everything keep going. And then eventually you can imagine a situation where the soil starts to dry out and the roots are like, uh-oh, we're in some problem here. We're running out of water. Abscisic acid gets synthesized in the roots in response to that, uh-oh, there's not enough water, and then it quickly courses up the plant body to the leaves. So thinking about leaf anatomy, and if you're trying to conserve water, what would you tell the leaves to do? Close the stomata, right? You want to conserve whatever water is left in your body as you enter into this drought period. And so that's what the abscisic acid does in a nutshell. It gets synthesized in the roots in response to the roots sensing not enough water, shoots up to the leaves, tells the guard cells, close that pore. And it'll keep it that way until the water balance in the soil starts to shift and you get a nice rain event or something like that, or you irrigate. Okay, so that's why you see abscisic acid accumulation going up. What about solute accumulation? So here you see under water stress, the plant is actually getting more solutes in its cell. It's synthesizing more solutes through gene expression. It can pick up some from the soil and get it into various parts of the plant body. Why would a plant want to make more solutes into its cells? Yes, it's playing with the osmosis idea, right? If you pack more solutes into your body, into your cells, water's going to want to rush into your cells by the laws of osmosis. You've shifted the delta C over delta X across those membranes. And so that keeps a positive flow of water into your body. If you start to accumulate more and more solutes in your cells, you're playing with that osmosis idea and you're forcing the situation where water will go into you rather than come out of you under drought. And so that's a very, very standard reaction that a plant will do. They'll start synthesizing a bunch more solutes to make sure it's a positive water flow from the soil into their tissues. So overall water potential measured in megapascals or pascals. If you're curious, other things you can measure that way too. So a car tire is typically inflated to about 0.2 megapascals for reference. If you're curious of how that would work, they give you some other values. So if it helps you to just kind of put things into perspective a little bit. So we said that water potential in the plant is either zero, but either zero or some negative number, all right? Because you have solutes involved in the situation. Plants have a size of S. Can't get away from that. What else? Oh, come on, there we go. So here is a graph showing some data that they took on the overall yield of their crop and how much water they were using. Okay, so on the x-axis is the amount of water that was being used by the plant, and then the biomass at the end. And so you can see they took two, barley and wheat, and you can see it's a positive correlation, right? More water, better yield. More water, better yield. More water, better yield. And you get that nice positive correlation. All right, so is there a point where you could flood the field? Sure, and natural flooding occurs too. And then some bad things happen. If roots get flooded for too long, it's like suffocating them, right? Because the roots still have to breathe, and oxygen doesn't flow very well in liquid water in the soil. So then they start getting not enough oxygen, and flooding can cause all kinds of issues, including a huge shift in what microbes are hanging out with the plant. And then that can be detrimental to the plant because the wrong types of microbes start to get high in population and can create some toxins and just nasty things that the plant doesn't want around them. We can talk about that kind of stress later in the semester when we get into abiotic stresses. Just a reminder that cell membranes have a way for water to flow through fairly quickly. You can have water molecule movement very slowly through the actual membrane, but they have aquaporins that hopefully you heard about that in basic BI 111. Perhaps aquaporins are the way that they can move through so quickly. And so those are protein channels that allow water movement. All right, so when we think about the typical plant, we are thinking about water in the soil system. The roots in the soil will take up that water and the dissolved minerals, and that's primarily through the root hairs, right? So here's an enlargement of a root hair in the soil particles, you got the water in the soil system, you have some air. And so now we have to think about water movement of going from the soil into the root hairs, and then eventually it's got to get to what vascular tissue, what part of vascular tissue? Vessels, and what's the other one? Starts with a T. Tracheids, and that's xylem. You're right, I heard all of it. So xylem is the vascular tissue. It has the tracheid and vessel options. And so we have to think about how all of that is going to happen next. I think that's in the next slide set with transpiration. So before we get out of this slide set, please go through this thought problem again. It's in the slide set toward the end, and see how comfortable you feel with this on your own. Also, there is in your book, I'm a little dismayed how they wrote it in the, I have it in my notes section somewhere, what page it is. I think it's page 56. They say, oh, because the volume of the beaker is so much larger than that of the cell, the tiny amount of water taken up doesn't really affect your components. So yeah, they got a point, but for practical purposes, for me wanting you to learn this concept, assume we always have a large water movement, which is going to play with your size of P and your size of S values. Okay, so I'm a little dismayed that they did it that way, because I want you to really think about what is happening to both components. When I say that, I'm talking about the size of P and size of S value that you have to add up to get your overall water potential. So if you go through some of these experiments, go over this one, come up with some of your own, and just see if you can play with what's happening, because I'll be asking you to do that on the exam and the quizzes in lab too, when you have a quiz on this material. So today's Wednesday. If you can get to it today, that would be awesome, because I just want to give you a heads up. This is never going away. For the rest of the semester, we're going to be talking about water potential. And if you don't get a grasp of this now, it's going to snowball in a way you won't like. Not to make happy snowmen, okay? It's going to be a bad feeling. So please do what you can to learn that. Yes. Well, the size of p-value, they'll explain about that. And then what you're going to end up doing at the end is calculating what the size of W value is at equilibrium. And so basically you're going to figure out what that will do for you then in the grand picture of the experiment is you're going to get a potato tuber, and you're going to be asked, what is the water potential of this potato? And so through this experiment, you'll be able to figure that out and say, and then you can think about when you finally get that size of W value of your potato, then you have to think about, well, is that a well-watered potato, or was it under stress? And maybe it's been stored for over a year or something before we got our hands on it. And so you'll be able to tell the water status of the tuber. So that, remember, potato tubers, they're living cells. They're functioning. So you're going to be figuring out its overall water potential. Correct. More negative. So size of W, if you end up with a pretty negative size of W, that means your potato's probably sitting in storage for quite a while and starting to dehydrate. Okay. Probably wouldn't make the best French fries. But there's so much more you can do with potatoes than French fries. Try to convince my boys of that. Potatoes are really good for you. Well, not so much the French fry idea, but if you cook them the right way, they're super good for you. All right. So please work through this. And if you can do that before Friday, because in Friday's lecture, I'll be going through it one more time, briefly, and asking if you have any questions on it. All right. So please, between now and then you'll get it again tomorrow in lab. So you have You know, we talked about it Friday, we're talking about it today, you'll get it in lab tomorrow, we'll get a review on Friday. We're hitting that topic that many times right now because this is never going away. And we want you to learn it, okay? All right, let's get into the next topic. Now, what happened to it? I gotta pull it up. I thought I had it all up and running. So now we're getting into the idea of transpiration, which is water movement through the plant. So I like this picture. It's like someone is laying on the ground looking up and they took a snapshot. And so we're thinking about what's happening in the soil system and how does the water get from soil to roots to eventually all the way to the leaf and then out through the pores of the leaf as water vapor. So it's quite the journey. And it's an especially tremendous journey if you're a giant redwood or sequoia. Massive, massive movements of water. So let's delve into the soil and think about what is happening in there. So soil water is not pure water. It hopefully has a bunch of minerals in it that the plant can access. So these minerals that are dissolved in the water, but you also have dissolved gases in the water. You have to think about whatever gases we have up here above the soil, it's the same below. Plus you have to add in, there's probably some pockets of concentrated methane and maybe some hydrogen sulfide gas and some other volatiles that the microbes and other organisms are kicking off as they live and breathe and do their thing in the soil. So here what you're seeing is a root hair, some soil particles, the water is blue, and then the white in this is an air pocket, all right? And so you have to imagine all those beautiful root hairs starting to take up the water and the dissolved minerals and gases and bringing them in to the root system that way. So as that's happening, if there's no new rain event coming along, eventually you can imagine where you're going to get bigger and bigger air pockets as the water is starting to get depleted in the soil, right? And so when you look at a soil system, and if any of you have taken soils or are currently taking the soils class, you're going to learn all about soil and how amazingly complex it is. It really does depend on what are the components of the soil. Is it heavy silt? Is it more sandy, clay? What types of clay? I mean, it goes on and on and on. This is just a tiny little example here of let's compare 4 different, like if it's predominantly coarse sand versus fine sand, silt or clay, and you're looking at the particle diameter comparison. So of course, coarse sand, very big particles, which means that they don't pack together very tightly in the soil system. And so water is going to percolate very easily through that, right? And imagine rain striking a coarse sandy soil. You're going to get water just percolating through. Those root hairs better be quick to sop up that water because very quickly it could go past the root system. Because of how many large particles there are, the water can flow through. It's also giving you surface area measurements as well. And you can see the smaller the particle size, like clay, the much larger the surface area of the particle is. And that can be really important for the idea that minerals in the soil system, they like to stick to the surface of the soil particles, whatever they may be. And so if you have a great surface area, that means you can put a lot of minerals on that soil particle. We'll talk about that when we get into mineral needs of the plant. But right now, let's focus on the water, not the minerals. Okay, so ideally you want a mixture. You don't want it all clay. If it was that way, then the roots couldn't get through that hard packed clay because the clay particles just pack together so well it can almost become like cement. But on the other hand, you don't want all sand. That's really tough on the plant as well. Well, the plant physiologists went into these different soil systems and they started measuring the water potential of the soil and the SISOBES and SISOP values. And what they were discovering is that the SISOBES value, pretty much of any soil system they were looking at, is near 0. Okay, so it's roughly around -0.02 megapascals. That's pretty close to 0. And so I like what they decided to do. They just said, let's ignore that component of the water potential. It's so close to zero, it doesn't really matter. We'll just call it zero, call it good. All right. So mainly what's going on is when you think about the soil system, you're mostly focused on the size of P idea of what's going on there. So that's great. It simplifies things. Well, when they started to take size of P values of these different soil systems, they were discovering if some negative number, well, that's weird, right? Or it's zero. So we've talked about size of P being zero in that open beaker. But here, we're saying it's a negative number. I didn't talk to you at all about a negative number so far. In the beaker, it's either zero. In the cell that we dropped into it, we had a positive pressure. Well, now they were measuring a negative number. Like, oh, okay, that's interesting. What's going on there? So if you look up the definition of the word tension, tension is defined as negative pressure, right? I do need you to know that definition. Simple. Tension equals negative pressure. So what that's saying is the soil system, the water potential is the size of P value. It's actually a tension force that's being created in the soil system, and it's a delta P over delta X. So it's a difference in tension in different parts of the soil system relative to the plant roots. All right. So let's think about that. Think about you being a plant with your roots in the soil, and you start taking up water into your roots. And as you're doing that, you're depleting the water right by your roots. Slowly over time, there's going to be more air gaps, less water, compared to bulk soil further away from you that isn't near your roots, right? So the water closest to you gets taken up first, and you're going to get this depletion near you. But further out, away from your roots, the water's pretty good still. So you're going to have a difference in the amount of water close to your roots, further away. And the way this gets created is that you will get a tension force developing. Higher tension right near the roots, less tension further out. So you get a tension gradient. You get a delta P over delta X, except instead of a positive pressure gradient, now we talk about a tension gradient. So higher tension near you, and I'll convince you how that gets established, and then lower tension further out in the bulk water, or bulk soil, where there's more water. So we're kind of going back to this idea of, if you can imagine a column of water in your hypodermic needle and then you pull back on it with the plunger, you're creating a suction or tension force on that water column. So that's what we're thinking about as water is flowing from the bulk soil coming to the root system. You have a tension gradient that is allowing for that to happen, where because of the plant's action of taking up water, it's creating a higher tension in the water right by its roots, in the soil water, right by its roots compared to further out. And so that tension gradient is going to keep the water flowing toward the roots. Have I convinced you? All right, I'll tell you the details of that next time, but we'll get into that on Friday. It is. Hang on just a sec.